All right, so today's lesson is probably the most important one in the first half of the simple harmonic motion and waves unit, okay? Because in this one, we're going to put together some things we've learned in other units to go along with this idea of energy being conserved in all motion, okay? So we're going to be looking at that this time in the context of a mass on a spring, which will bring in a new type of energy for us, okay? And then also in the form of a pendulum, which doesn't bring in any new forms of energy. A pendulum relies on the same forms of energy as a roller coaster does. Okay? So if I was doing a law of conservation of energy question on a pendulum, I would solve it just like I would for a roller coaster. I'd have gravitational potential energy, I'd have kinetic energy, and I'd be solving for either a height or a speed or something like that. When we're dealing with a mass on a spring, we have different kinds of energy. We still have kinetic energy because the mass on the spring is actually going to be moving. Okay? But its potential energy isn't gravitational now, it's elastic. And that's dependent on different things. Okay? Then obviously gravitational potential energy is, that'll be the bulk of our focus today. Okay? So we need to understand, first off, the relationship between restoring force, which we talked about when we talked about mass on a spring and a pendulum. The restoring force is the force that brings the object back to equilibrium. It's always trying to restore equilibrium. For something undergoing simple harmonic motion, that restoring force varies linearly with displacement from equilibrium. So that means the more I stretch that object, okay, the further I pull it from equilibrium, the more force it's going to pull back with. Now, that would also seem to fit with another idea. If I push it further and further away from equilibrium, if I'm talking about a mass on a spring, it's going to have more and more of what kind of energy? Potential energy. It's going to have more restoring force, and thus it's also going to have more energy, because energy or changing energy requires work. How do I calculate work? Force times distance. If I compress a spring, am I exerting a force through a distance? Okay, so that's what we're going to be looking at. So Hooke's law is the first thing we're going to look at. Hooke, this is the same Hooke who invented the microscope, by the way. Okay? Hooke was a physicist, right, by trade. He invented the microscope purely as a lens experiment. Okay, which just goes to show that physics is the most awesome of all the sciences, because it provided another science with its most important tool as an exercise. Okay, it wasn't even trying to prove anything. Hey, what happens if I put these lenses together? Hey, biology, you didn't figure this out for yourself. Physics is awesome. Yeah, that's right. You can tell your biology teacher that. They all know biology is not the coolest science either. Okay, all right. So we got to understand that energy is obviously conserved in simple harmonic motion if we're talking about the perfect physical world, okay? And that potential energy in simple harmonic motion is elastic potential rather than gravitational. That is for a mass on a spring. For a pendulum, it's obviously gravitational. Okay, so here's what Hooke discovered. Hooke took this spring that he had and he hooked it on the ceiling and he measured how long it was. And then he put 100 grams on it, and the string stretched. Okay? And then he put 200 grams on it, and the string stretched
Further.
even further. How much further?
2 times.
Twice as far. Okay? And so he discovered then that the restoring force, or the elastic force in a spring, is equal to negative K, which is the spring constant we talked about last week, times X. X is our displacement from equilibrium. I know that's weird because every other time we've done displacement it's been D. Okay? But that's displacement from position 1 to position 2. Because an object with simple harmonic motion can be displacing itself in either direction, we use X. Okay? So it's going to be negative K times X. That'll get me the force in the spring. Now remember, spring constant is how stiff the spring is. It's measured in newtons per meter. Okay? So if I perform this multiplication operation, I'm going to be multiplying newtons per meter by, what are the units for displacement? Meters. What's going to happen to the meters? They're going to cancel. I'm going to get this force in the spring. Okay? Newtons. Yeah. All right. Now, what's the negative for? The formula always has a negative in it.
Because it's going up, not in.
you're on the right track. If I displace a mass on a spring, if I push it to the right, which way does the spring push?
Away from you.
Left. Yeah. Okay? The negative has to be in there because force is a vector quantity, so is displacement. Okay? And it has to make sure that the force is going to be directed opposite the displacement. By putting a negative sign there, your force will always be opposite your displacement. So if I displace the mass on the spring to the right, the spring pushes to the left. That negative makes sure it's always opposite. Okay? Everybody all right with that idea? Is Hooke's law a very difficult formula? It's really, really easy. Okay? The thing you have to remember about Hooke's law, or the thing you have to get the hang of, is determining when you actually need to use it. Because it's going to give you similar information to these law of conservation of energy questions you're going to look at next. What's it say? It's different for every spring. It's the statement of the spring, so it's unique. It's specific. No, it's not a set number. Not like big G. It's different for every spring. Okay. So, stated mathematically, Hooke's law is force equals negative k times x. Now, if I have this situation here where the spring is horizontal, okay, and it's on a frictionless surface, that restoring force is the only force acting on the mass, which would make it the, not normal, starts with N, net force. It's the only force acting on the mass, so it is the net force. So lots of times we'll see negative k times x set equal to m times a. Would that allow us to calculate the acceleration of the mass? Yes. Okay. We can calculate the acceleration of the mass using Hooke's law because the restoring force is the only force acting on the mass on the spring. Okay, so we're going to see situations where that happens. What if the mass is hung like it is in this situation? What's the net force here? Well, gravity's involved, but if I just hang this mass here and it's not moving up and down, what's the net force? Zero. Okay, so then that would say then that negative k times x is equal to m times g. Okay, they're balanced. One acts down, the other acts up. Okay, and they would be equal. So if you have a hanging mass that's not oscillating up and down, okay, then your spring force is offset by the force of gravity, or is being provided, and or is resisting the force of gravity with equal opposite force. Okay, so that's a situation we're probably going to run into a few times here where it's either going to be the net force, or if we're talking about a hanging mass, it's going to be the force of gravity pulling down on the mass and the spring resisting it. Okay? All right. Now, in terms of energy, okay, elastic potential energy is the energy stored in any object that when deformed will try to return to its original shape. Okay, spring is a prime example. If I stretch a spring or compress a spring, I'm deforming it. I'm exerting a force through a distance, and I'm making it so that it wants to go back to its original shape. Okay, a bow and arrow, similar. Okay, if I pull on the string, the ends of the bow get closer together. The bow doesn't like that. It wants to go back to its original shape. That's what pulls the string forward when you release it. Right, Ben? So that's it. Okay. Everybody follow me there? All right, now this is our formula for calculating elastic potential energy. Okay, 1/2 times the spring constant times the displacement squared. Okay, now I'm going to show you where we get that from. I don't know if you guys remember this, but back in Science 10, most of you anyway, would have done a lab where you had an elastic band strung between the legs of the desk, and you pulled on it with a spring scale. Okay? You picked some distances and you measured the force that was used to pull the rubber band to these various distances, and then you calculated the work you had done. Okay? So you got a graph that was shaped like this. Okay? It's just obeying Hooke's law. It's saying that as displacement increased, sorry, you had D down here, but D is X for us. Okay? As displacement increased, so did the force, according to Hooke's law, negative k times x. Okay, the force got bigger as x got bigger. The slope of the line would have actually been k. Okay, it would have been the spring constant because it would have been dividing newtons by meters. Okay. Now, in that lab, you were required to find the work done on the elastic band. So you found the area under the line. Okay. When I do that, how do I calculate area of a triangle? Base times height divided by 2. Okay, so the base is in what units? Meters. And the height is in newtons. Okay, so it's in, right, it's force. Now, I'm supposed to go base times height over 2, okay, and I'm multiplying a force by a distance. Now, that force that's here is actually this force. Okay, but I'm not using all of it, I'm only using half of it, because it's 1/2 base times height, so base times height over 2. Well, if I take 1/2 of this and multiply it by this, that's where that formula comes from. I'm calculating the area under the line, or the work being done on the elastic object. Okay? The work done on an elastic object has to equal the amount of potential energy that it contains after. That's work energy theory.
How do you recognize the string one over the potential energy one?
String one over.
Like the force of the spring over the potential energy. Like how do you recognize how do you recognize the first one over the potential energy one? Like if
Oh, how do I tell if it's this kind of a situation? I haven't got there yet. Okay. Yeah, but you're ahead of me. Come back. I'm not there. Okay. The short answer to that is it gives you slightly different situations or slightly different numbers. But we'll get to it. Yeah. Okay, everybody with me on how we kind of derive that formula? Okay, that's why with that lab in Science 10 is so important. I know it seemed like a really podunk kind of lab. Stretched a rubber band and measured the force. Seemed pretty silly, but this is why. Okay, it leads to this idea of elastic potential energy in Physics 20. All right, now, if I have no displacement, that is, the spring is neither stretched nor compressed, then it doesn't have any what? It doesn't have any force, and it doesn't have any energy. Okay, if x is 0, okay, then it has no potential energy because it has no force. Okay, there's no force, there's no distance, there's no energy. Okay, as soon as I apply a force and stretch it or compress it, then there is elastic potential energy involved. Okay. So, the law of conservation of energy is exactly the same as it was before. It's still EI equals EF. Okay, it's still initial potential plus initial kinetic equals final potential plus final kinetic, just like when we did this for a roller coaster. All that changes is now, instead of having m times g times h for our potential, now we have elastic potential instead. Everything else works exactly the same. Okay? You're just, instead of now possibly manipulating for a height, now you're going to be manipulating for a distance from equilibrium or displacement from equilibrium. Okay. Now, when this object is going back and forth, and we talked about this the other day, but we need to review it. Okay? When it's way out here at its point of maximum amplitude, amplitude means the maximum distance from the center. Okay, any distance from center is just displacement. The maximum is the amplitude. So when it's out here at its maximum amplitude, its speed is 0. Because what has the spring been doing the whole time? Just slowing it down, pushing against it, or pulling against it. Okay, so it slows it down, Now at that point, its speed is 0, and its acceleration is at its maximum. Right? The reason its acceleration is at its maximum has to do with this. The only force acting on it is the force in the spring. And this is at its maximum value. That's as far from equilibrium as it can get. Okay? So its acceleration would be at its maximum there. The restoring force would be at its maximum, and its potential energy would be at its maximum. What's the kinetic energy? Okay. As the mass begins to move back towards equilibrium, its speed increases. Okay? The force acting on it decreases. Okay? And it decreases until it gets back here to equilibrium. Now, the whole time it's been traveling towards equilibrium, it's been accelerating. So now it's at its maximum what? speed. Okay? It's been pulled from rest at its maximum amplitude towards equilibrium where its speed is at its maximum. Okay? At equilibrium, what's the acceleration? 0. Okay? The acceleration at equilibrium is 0 because now the spring is neither stretched nor is it compressed. Okay? So it can't exert any force because x at equilibrium is 0. And remember, x is the displacement from equilibrium. So when we're at equilibrium, x is 0. There's no force, there's no restoring force, there's no acceleration. There's no elastic potential energy. So that means all of the mechanical energy of the mass is now in what form? It's kinetic. Okay? We just said a minute ago, it's now moving at its maximum speed. If it's moving at its maximum speed, now all of its energy is kinetic. Okay? All right, and then as we move away from equilibrium, we start compressing the spring again. As soon as we start compressing the spring slows the mass down, changing kinetic energy into potential and having an ever-increasing amount of force, an ever-increasing acceleration, ever-decreasing speed until we get to amplitude on the other side. Okay? And the whole process starts out again back towards equilibrium. So that restoring force is always fluctuating. Okay? It's getting bigger and bigger and bigger, and then smaller and smaller and smaller, bigger and bigger and bigger, smaller and smaller and smaller. It's just always fluctuating as the object moves through. And as it's doing that, it's constantly converting kinetic energy into potential and vice versa. Just like a roller coaster going up and down the hills, okay? The mass on the spring is doing exactly the same thing. All right, now, back to Robert's question. How can I tell the difference between a law of conservation of energy question and a Hooke's law question? Okay, the answer to that is this. A law of conservation of energy question always has to compare 2 points. Okay, you can't do a law of conservation of energy question unless you can equate initial energy to final energy, which means you have to be comparing 2 different points in the motion. A Hooke's law question is only dealing with 1 position. Okay, so that's basically how you tell them apart. Okay? A Hooke's law question will always talk about an object in only 1 position, and oftentimes it's not moving. Okay? Obviously, for a law of conservation of energy question, the object has to be oscillating. Okay? All right. So we're going to look at a few examples here of both Hooke's law and then a few of law of conservation of energy, and let's see how we do that. Okay. That one we're going to skip because that's the one I already went over. Okay, that's our work lab from Science 10. Okay, displacement, force, okay, all of that kind of stuff. Okay, so I have a spring that has a spring constant of 30 newtons per meter. So they just gave me, okay, the spring is pulled 1.50 meters from equilibrium. What did they give me there? X. Okay, what is the restoring force? Okay, what formula calculates restoring force? Right, Hooke's law. F equals negative K times X. Okay, now here's the thing they don't do. They don't tell me, maybe they do in the picture I forgot to bring over, okay, which way this object is being displaced. Is that kind of important? Yeah, force is a vector quantity, and so is displacement. So all I'm going to be able to do here is say that this is positive. Now my force will be negative, and that's okay. It should be opposite. All right, so I'm going to go negative 30 times 1.5. So I should get negative 45 newtons. The force should be in the opposite direction of the displacement.
Since it's like a vector quantity, where would we say like the direction's going?
In this case, I can only give negative. They didn't give me, probably the picture would have showed it, but I didn't bring the picture. It says shown in figure 7.17, but I didn't bring the picture of it. So maybe it didn't, maybe it said that's positive and this is negative, I don't know. Okay, I'm just going to say that was positive. Then all I can do is positive and negative. That's all I was given. Right? If it was up and down, then I give up and down or left and right. Okay, everybody all right with that one? Okay. So, I want you guys to try these 2. Hooke's law is not mathematically difficult, so I don't think you'll need too much time on this one. Okay, we're going to look at this one together. So I have a spring, and it's hung from a hook on a ceiling, just like what Hooke did. Oddly enough, because it was hung from a hook. Okay, we put a mass of 510 grams. Okay, that's 0.510 kilograms. Okay, we put it on there, and the spring stretches half a meter. Okay, so this is a Hooke's law question, and the way I can tell that is because what's the spring not doing? It's not oscillating. It's just stretched. Okay, so the net force here is 0. Okay, in a law of conservation of energy question, the spring would be moving back and forth. The net force would constantly be changing. Okay, and we wouldn't have that situation. All right, so I've got this. Now, the only reason the spring is stretching and exerting a force is because of what other force? Gravity. Gravity is pulling down on the mass they hung from that spring. Okay? Since it's not moving, those forces cancel each other. One is up, the other is down, and it's not moving. Okay? So can I now calculate what K is? Yes, I can. Okay, so I'm going to divide both sides by X. Okay? And I'm going to bring the negative over, so I'm solving for a positive K here. Okay? Now, is my X up or down? Yeah, it's down. Okay? But then, so is gravity. So, here's the problem. This number's negative, that number's negative, and I'm multiplying by a negative. So I'm still going to get a negative. But K can't be negative. K is an absolute value. It's just the stiffness of the spring. It's neither positive nor negative. This only happens once in a while. Whenever you solve for K, you're solving for the absolute value of K. If you get a negative number, it doesn't matter. Okay? It's just because it was a weird situation where the vectors went crazy. Okay? K is never positive or negative. K is just a value inherent to each spring. Okay? So in this situation, we're going to have 0.510 times 9.81 divided by 0.5. Okay? And that'll give us our spring constant. Okay, so 0.51 times 9.81 divided by 0.5. All right, so the spring constant of this spring is 10 newtons per meter. Okay. So anytime you have a spring question where something is hanging, okay, then it's going to be a Hooke's law. Okay, where it's just hanging. If it's oscillating, that's different. That'll be conservation of energy. But if it's hanging, okay, it's not moving, it's going to be a Hooke's law problem. Okay, one of the prime places where we use this is at, like, if you go to the grocery store and you ever weigh your fruit in the scale, the hanging scale. This is what they use. They use Hooke's law to weigh your fruit. Okay, there's a spring inside of that thing, okay, that makes the dial turn. Right, and that's all they're using.
So if you break the spring, you can get a cheaper version.
Yes. If you break the spring.
Or just replace it.
Well, actually, no, it wouldn't. If you broke the spring, it would stretch further and tell you it was heavier, and you'd actually pay more. Yeah. If you deform the spring. Yes, if you put in a harder spring, it wouldn't stretch as far, and then the dial wouldn't move as far. But I think they would notice you tampering with it, and what's on that scale is not the scale they use at the register, right? They reweigh it with the digital ones today. So, the scales that are out there are just there to give you a ballpark of how much do you have. It's especially important if you buy a bag of cherries, right? Like in the summertime, you look at this bag of cherries, and it's like, and they have the price per pound, not the price per bag. So it looks like it's a great deal because it's a big bag of cherries, and it says like $2.97, and then really fine printing per pound. So you walk up to the register, and they're like, "That's $18." I'm like, I don't want to buy $18 worth of cherries. Well, that was the price per pound. Oh, that's nice. I don't want them. Good. And that one we're going to skip. We're going to skip that one too. Okay. Let's try number 1 here. I want you guys to write down number 1, and we're going to walk through number 1 together. Okay, so write it down here. Okay. So for question number 1, it's asking us to calculate the acceleration of the mass. Is that a Hooke's law question or a conservation of energy question? Have you ever been asked to calculate acceleration in a conservation of energy question? No, because you can't. It's always changing. Okay, especially in this kind. So it has to be what kind of question? Hooke's law. How many pieces or how many places are we talking about here? 2. Okay, it's oscillating on a horizontal frictionless surface attached to a spring. What is the mass's displacement when its acceleration is this much? It's only talking about one place. Okay, it's not trying to compare 2 places. Okay, that's the way you tell the difference between a Hooke's law question and a conservation of energy question. It's talking about one position, and it's asking about something you cannot calculate using law of conservation of energy. Right? So in this case, because it's on a horizontal frictionless surface, our net force is equal to our restoring force, the force in the spring. M times A equals negative K times X. They give me K, and they give me the acceleration. They also tell me the mass. The only thing I don't have is the displacement, and that's what they want me to find. So I'm going to divide both sides by negative K, okay, and solve for X. All right, now, on this question here, it is saying that the acceleration is to the left. All right, so right's going to be positive, left's going to be negative. All right, so I'm going to make this number here negative. Will that work out? Yeah, because I'm going to divide negative acceleration by negative K, and that'll give me positive X. And X should be opposite the force, okay, and opposite the acceleration. So I'm going to have 0.724 times my acceleration, which was 4.11, okay, divided by the spring constant, which was 8.2. So 0.724 times 4.11, okay, divided by 8.21. All right, so the displacement is going to be 0.362 meters. Okay, to the right. The acceleration is left, then the displacement is to the right. Okay. Number 2. How many different positions are they talking about in number 2? One of the positions mentioned is the point of maximum amplitude. And then they want to know the maximum speed. Where does the maximum speed occur? In the middle. He's just talking about 1 or 2 different places. 2. So it's a conservation of energy question. It's asking about 2 different positions. Okay? You have to read questions carefully. The math of this is easy. You've been doing conservation of energy since grade 10. Okay? But getting what you need is what's important here. All right, so what we're talking about is EI equals EF. Okay, so that's going to mean the initial potential plus the initial kinetic equals the final potential plus the final kinetic. Are any of those forms of energy 0? Yes. How many of them? 2. Okay, the first point we're told about is the point of maximum amplitude. Okay, at the point of maximum amplitude, how fast is the object going? Okay, so we don't have any kinetic energy there. And when it's moving at its maximum speed, it's at equilibrium, where there's no what? There's no potential. Okay, so now we can say that 1/2 kx squared equals 1/2 mv squared. Okay. the maximum potential equals the maximum kinetic. And that's the base of all conservation of energy questions. The maximum of this, the mechanical energy never changes. Okay, so I'm trying to solve for its maximum speed. So I'm looking for V. What do I have to do with the half and the m? Okay, or I could just divide both sides by half of m. What happened to the halves? Okay, what else do I have to do? Square root. Okay, so V will equal the square root of 4 newtons per meter times the displacement, 1.12 squared, divided by the mass, which was 50 grams. That's 0.05 kilograms. All right, so 4 times 1.12 squared, and divided by 0.05, and square rooted. All right, so the maximum speed of that object is 10.0 meters per second. Okay, I think you guys can handle number 3. You're given the maximum displacement, you're given the maximum speed, and asked to find the mass. You are also given the spring constant. Okay? What kind of question is it? It's a conservation of energy question, because the maximum amplitude and the maximum speed occur at different places. All right, I'll give you a little bit of time on that one. All right, so on number 3, okay, we've got, again, a law of conservation of energy question. Okay, and it's an oscillating mass spring system. We know what K is, right? So K is going to be 6.05 newtons per meter. Okay, the maximum displacement, so our X, or actually our A, amplitude, okay, is 0.817 meters. And our maximum speed is 2.05. Now, why am I bothering to label them differently? Why am I not just saying X and V? Right, like V could be other numbers. If I'm not dealing with the maximum amplitude and the equilibrium position, I'll have a V. Okay, I'm saying this is the maximum V can be. Right? I could also say VF and just go with I, but okay, I want to denote that this is a special displacement, the maximum. This is a special speed, the maximum. Right? So we're going to have then that 1/2 Ka squared equals 1/2 MV max squared. Right? And we're trying to find here the mass of the object. So the halves are going to cancel, and I'm going to bring V max over, V max squared. Okay, now I'm solving for m, right? So all I have to do is go 6.05 times 817 squared divided by 2.05 squared. Most common mistakes here, guys, are forgetting to square things when we're doing our math. Okay, and then we divide that by 2.05 squared. Okay, so we're looking at a mass here of 0.646. Okay, whoop. Did I type something wrong? I did. I put 2.5 instead of 2.05. That's better. 0.961. Okay, did you sign in at the office? Huh? Did you sign in at the office? Okay, everyone got that one? All right, so we've got this one here that's going to combine 2 things we've talked about. It's telling us the period. We're looking for the period of the oscillation of this mass on the spring. Now, for a mass on a spring, we calculate the period with this formula. Okay, but this is clearly a law of conservation of energy question as well, because they're telling us about maximum speed and maximum amplitude. So maybe there's some part of this formula that I have to solve for using law of conservation of energy before I can solve for the period. I'm going to give you guys a few minutes to try that one before I do it up here. Okay, so here's what we know. This mass is oscillating back and forth. They want us to calculate its period. The problem is, I don't know what the mass of this object is. Okay? I can't use this formula to find its period until I know what its mass is. But because it's oscillating back and forth, okay, I can use the law of conservation of energy to calculate its mass. Right? One of the points they talk about is the point of maximum amplitude, where all of its energy is what kind? Potential. It's where the spring is stretched the most, okay? And where the object has a speed of 0. All right, so 1/2 k times the maximum amplitude squared equals the other piece of information they gave you, the maximum speed of the object, which occurs at equilibrium. Okay? So I know what Vmax is, I know what A is, I know what K is. I can solve for M. The halves are going to cancel, okay? And just like the last question we did, I'm going to have Ka squared over the maximum speed squared to give me my mass. So that'll be 5.03. That's the spring constant, times 0.1225 meters squared, okay, divided by 5.13 squared. All right, so this is an incredibly small mass. Okay, it's like 2.8 grams or 2.9 grams. It's incredibly small. Well, that's fine. Now that I know what it is, I can use it to calculate the period using the formula for period of a mass on a spring. Okay, so now I'm going to plug that in, and we're going to have 2 times pi times the square root of my answer divided by the spring constant, which was 5.03. Okay, so the period of this oscillator is 0.15 seconds. Right? Is that pretty fast? Yeah, this thing would be just a blur if you were watching it. Okay, it's moving out 12.5 centimeters, back 12.5 centimeters, okay, and back to that point again several times per second. Okay, so it's a small mass on a pretty heavy spring. Okay, and it's moving back and forth very, very quickly. Yeah, absolutely. Okay, so is it possible then to get something that would combine more than one concept into one problem? Yeah, it is. Okay, probably not on an exam, but certainly on like an assignment or a worksheet or something like that, you could run into a question that asks you to do 2 different things. Okay, I want you guys to try for right now just question numbers 1 and 2. Okay, so you're going to have to do a little bit of Hooke's law, a little bit of conservation of energy, okay, and then a period calculation after that for question number 1. So I'll give you a few minutes on that one. Okay, so for number 1, here are our givens. We have a mass of 2.5 kilograms. Okay, and it's oscillating with an amplitude of 0.800 meters. Okay, the spring constant's 40 newtons per meter. All right, we want to find the acceleration of the mass when it is at a displacement of 0.3. All right, so they're giving us another displacement here, 0.300 meters. And they only want to know the acceleration. Would I use conservation of energy to find that? No. What will I use? Hooke's law. Okay, this is a horizontal spring, so the net force is the spring force. Okay, so I want to find what's the acceleration. All right, now they're also telling me no directions here. Okay, they're just saying when it's at a displacement of, so I can't really give a direction. They didn't give me any directions, left or right or whatever. right? So I'm going to divide both sides by mass to solve for acceleration, okay? And so that'll be 40 times 0.3 divided by the mass, which was 2.5 kilograms. Right? When I do that, okay, so I'm getting 4.8 meters per second squared. Again, I can't give a direction on that because they gave me no direction on that. Right? So sorry, 4.8. Yes, Steve?
What happened to the negative?
You know what? Because I didn't have any direction, I just took it off. I couldn't solve for a direction, so I just ignored the negative. Okay? If they'd have told me the displacement was left, then I would have left the negative on. This would have been a negative, and I would have gone negative times negative is positive, and I would have got right from my vector.
So you make x negative 2?
Well, if it was left, yes. Right? Left and right. All right, meters per second squared. All right. Part B, looking for the maximum speed. So I have the maximum amplitude, I have the mass, and I have the spring constant. Okay, can I use law of conservation of energy to get the maximum speed?
Yeah.
Yes, I can. Okay, it's 2 points. So I'm done with Hooke's law for now. Okay, now I want to solve for the maximum speed. So that'll be EI equals EF. Okay, and again, so we'll say initial potential, okay, plus initial kinetic equals final potential plus final kinetic, but two of these are 0. Okay, initially we're at the maximum amplitude where our speed is 0, and at the end we're at the maximum speed, which is at equilibrium, where there's no potential energy. Okay, so I'm going to have 1/2 k times the amplitude squared divided by 1/2 mv max squared. So I'm solving for the maximum speed. The halves are going to cancel. I'm going to divide both sides by m and square root. Okay? And so I'll have 40 times 0.8 squared divided by 2.5. Okay, so the maximum speed of this thing is 3.2 meters per second. Okay, everybody all right with that? Okay, the last thing it wants me to find is the period. Now, do I need Hooke's law or the conservation of energy to do that? No. Okay, I don't need either one of those to solve for period. All I need is mass and spring constant, and I already have both of those. They're here and here. So T equals 2 pi times the square root of m over k. Okay, so 2 pi times the square root of 2.5 divided by 40. Okay, and so we're looking at 1.6 seconds, or 1.57 seconds, okay, as our period. All right, everybody all right with that? How many people have done number 2? Okay, I want you guys working on 2 and 3 right now then. Okay, so what we have is that the spring constant, or the spring force, k times x, equals our net force. Okay, it's the only force that's acting in this system. Okay, so that has to be the net force. I need to solve for the spring constant. So I'm going to divide both sides by x. Again, they gave me no directions here, so I'm just going to solve for an absolute value anyway. Okay, k is never positive or negative. Right, so we're going to take our mass, 0.0026, times our acceleration, which is 20, and divide that by 0.7, which was the displacement, and that should give us a spring constant of 0.0743 newtons per meter. Okay, that is an incredibly light spring.
It's like a 10 spring.
Or even lighter than that. Yeah, very, very light. Okay, question number 3. Okay, my No, that should be pretty straightforward, okay? We're just looking for, we have period and we're looking for mass. Okay, we have period and spring constant. We should be able to find mass for number 3. I'll give you another minute or two on number 3. All right, so for question number 3, okay, we're looking for the mass. Okay, we're told the spring constant is 20 newtons per meter, and we're told the period is 2.0 seconds. So T equals 2 pi times the square root of m over k. That's all I need to use. I don't need to use conservation of energy or Hooke's law here. Okay, I have the information to use this formula instead. So I'm going to solve for m by first squaring everything. 4 pi squared times m over k, and then I'm going to move everything over to the other side except for m. Okay, that'll allow me to solve for m, so that'll be 20 times 4, 2 squared, okay, divided by 4 pi squared. So 20 times 4 pi squared, okay, divided by, 20 times 4, which is 80. I don't know why I just put that in. Okay, 80 divided by 4 pi squared, and I need to put that in brackets. Okay, so the mass here is 2.03 kilograms. Actually, we only have 2 significant figures, so it's 2.04. All right, how many people have done number 4? Okay, working on number 4, because tomorrow's quiz, since it's Tuesday, okay, will be on simple harmonic motion. There could be some Hooke's law stuff. There will definitely be some stuff involving the period of a mass on a spring and the period of a pendulum. Right? So that's what you need to be on the lookout for. I will post that later on today. Okay, well, let's work on number 4 to finish off here.